In this lab, you're going to look at both analog and digital signals using a virtual oscilloscope. Let's get started. Here are some examples of digital signals, also called square waves or clock signals. Now notice that what makes them a digital signal is that their value is either 0 volts or some non-zero value, typically 5, right? They go between 0 and non-zero, and most often you will see that it's between 0 and 5 volts. Here are some examples of analog signals. Notice analog signals have a minimum and maximum that can either be positive or negative, as in this case. These are negative voltages down here and positive voltages up here. Typically, analog signals will look like sine waves, like this first example, but they can also be square waves. This is not a digital signal. The reason it's not digital is because it has a negative value right here. Remember, digital signals always go between 0 volts and some positive non-zero value. Let's go over the parts of an analog signal. The amplitude is just the distance from the center line, in this case 0 volts, up to the highest point of the wave. Sometimes they refer to peak amplitude. That is just the measure from the very, very highest point down to the very, very lowest point. It's always twice of what the regular amplitude is. The period, I always think of time period. The period is how long it takes the wave to complete one full cycle. So in this case, let's say these big distances here, let's say this is seconds, the period of this wave would be 2 seconds, right? It takes 2 full seconds, 1, 2, to complete a full cycle. Frequency is the reciprocal of period. Frequency is cycles per second. So if the period of this wave is 2 seconds, the frequency would be 1/2 or 1/2 cycle per second. And if you look at it, it makes total sense. This wave completes half a cycle per second, right? 1/2 cycle per second. Its period is 2 seconds. Remember, frequency and period are reciprocals of each other. All right. Now let's take a look at the parts of a digital signal. I know this looks like a lot, but most of this is such common sense, and it's really very similar to the analog signal we just looked at. The amplitude, of course, is just the height of the wave. It's measured from 0 to the very top, and this is almost always going to be 5 volts in the digital signals. The digital signals that we look at. Period, again, it means the same thing as it does in an analog wave. Period is just how long it takes to complete one full cycle. So here, the period is from this very start right here up until the same point, right? This is one full cycle. That's my period. Frequency, again, is just the reciprocal of period. So if the period is t, the frequency right down here would just be 1/t. That's pretty simple. These other terms are also very, very simple. The time high is just what it sounds like it is. It's the amount of time that the wave is up high, like this guy right here. That's the time high, and you'll never guess what time low is. Time low is the amount of time that the wave is down here at 0 volts, time low. The duty cycle, that's a percent. That is just the percent of time that the wave is up here high, right? What percent of the time is it up here compared to the entire length of the wave is really what the duty cycle is. 2 more terms. The rising edge is just like what it sounds like it is. It's the transition from 0 volts up to 5 volts. And of course, the falling edge is the opposite. It's the transition from 5 volts down to 0 volts. And again, I know there's a lot of terms here, but really they're all pretty much common sense. Finally, let's measure some values in a digital signal. First, the amplitude, of course, is just the height of the wave. That's the y along the y-axis. So I'll look at the little y position scale, which it tells me is 2 volts per division. So every time I go up one of these lines, it's 2 volts. So that is 2, 4, and then half of a big line, that's 1 more. The amplitude is 5 volts. Well, you know it's almost always going to be 5 volts for digital signals. Now let's take a look at the period. Of course, period is just the time it takes to complete one full cycle. So I want that distance right there. And it tells me that's along the y-axis. So the y scale is 2 millivolts. That's what ms means, millivolts per division. So that is 2, 4, 6, 8. It looks like 8 milliseconds is my period. 8 milliseconds. That's it in engineering notation. Of course, frequency is just 1 over period, but I need to express it in milliseconds. Don't mess this up. When I put it in the equation, you need to put it in terms of seconds. I'm moving the decimal point 3 places over, right, to go from milliseconds to seconds, right? Move it 3 places over. So 1 over 0.008, I already did that in my calculator. It is 125 cycles per second. The units, again, is hertz. I'm putting Hz. That is my frequency. Time high is just how much time the wave is up high, like this. It looks like 2, 4, and then how many of these little notches? They go by 0.4s there, so 0.4, 0.8. So the time high is 4.8 seconds. The time low is just this distance from here to here. That looks like 2, and then that goes by 0.4s again, so that must be 3.2 totally. Let's say 3.2. I know if that works, that if I add up 4.8 and 3.2, I should get the total period, which is 8. Well, yeah, that worked. Oh, I'm sorry. These are milliseconds. I'm writing S for seconds. These are really milliseconds. Milliseconds. And then finally, the duty cycle is the percent of time that is high, right? So it's up for 4.8 milliseconds. And the total period is 8. So 4.8 divided by 8, and then of course times 100, that converts it to a percent. That comes out to 0.6 times 100 is 60%. So the duty cycle, again, the duty cycle is a percent of time that it's up high. The duty cycle here is 60%, and it looks like that. It's a little bit more than half the time the wave is up high. So that's it. So it's now your time to give it a try, and you're going to do a lab very similar to this, and should be a piece of cake.